this, and we identify it as being a absolute value equation. What do I have to do first? Say it again. Yes, I have to clean it up. I have to add 9. So 1 minus 3x divided by 2 equals good. And then I know that there have to be two options here, right? So I'm asking myself, which numbers have the distance from 0 exactly 3? So I know that this changes into, I cannot solve it, and you don't have to do that. I'm just trying to make a point, make you remember, or help you remember. What are the two options? 1 minus 3x over 2 to be 3, or 1 minus 3x over 2 to be negative 3. Perfect. Then how do I solve the first one? Multiplying both sides by 2, and then the other one. So when I multiply both sides by 2, I get 1 minus 3x equals 6. I subtract 1, and I get that x equals negative 5/3. And that's the first possibility. The second possibility is 1 minus 3x equals negative 6, or negative 3x, I move 1, equals negative 7 and 7/3. Is this okay? Yes? Any questions? Is this okay? Perfect. So now we are finally ready to start chapter 10. And remember, on Tuesday, I may still ask you a couple of questions, couple of quizzes on chapter 9. So try to finish chapter 9 completely so we can move on. Okay. As I mentioned before, I created this handout actually this semester because I think that this chapter is not necessarily difficult. Students do better on chapter 10 than on 9. I have no idea why. For some reason, they get this chapter 10 much better than chapter 9 for some reason. And in chapter 9, many people just connect things differently. They write solutions out of the blue. I'm not sure why. That was from my experience. So it's not a difficult chapter, I think, but it has a lot of little rules that we have to learn and master and be able to apply. So now, from the very beginning, I want to say that these two are together. Forget about this. This is something at the very end of the chapter. These two are together because they are the same. How is that possible? I'm telling you that a radical can be changed into an exponential notation with rational exponents. And I'm telling you that, in other words, vice versa, an expression with rational exponents can be changed into a radical. They don't look the same, but they are the same. So keep that in mind. I'll come back to this in a second. Now let's define the radical notation first. So this is chapter 10. Do you all have this handout? How do you have it? Okay, just making sure. I don't remember if I gave you one. Okay, so this is the notation, and let me tell you how we read it first of all. This is lowercase n, and this is lowercase m. So here's how we read it. The nth root of a raised to the mth power. It's a lot, right? The nth root of a raised to the mth power. What are these pieces involved in this notation? It's a notation. As an example, you know that I can write 1/2 as 2 to negative 1. They mean the same thing. Same thing here. A radical can be changed into an exponential notation with a rational exponent, and anything that has an exponent that is a fraction is a radical, actually. Okay, so these two are the same. Same thing here. 1/2 is the same with 2 to negative 1. You can say, wait a minute, why do I really need two notations for the same thing? Well, sometimes this is more convenient than this. Sometimes this is more convenient than that. So it depends on what I have to do. I cannot add exponents. I cannot add quantities with negative exponent. I have to change them into fractions to add them. So it all depends. This may be more convenient than this. The same thing here. The radical may be more convenient than this sometimes, and this may be more convenient than the radical sometimes, depending on what I'm trying to do. If I simplify, maybe this may be better. If I solve a radical equation, this may be better. So it depends. Okay, coming back here, let's identify all these pieces. This little n is called the index. The index of the radical is a natural number, and it can be 2, 3, 4, and so on and so forth. Now, this is what is called the radical symbol. This. So it's the radical symbol. And this quantity, and we have to remember this, it has a special name, or a name. It's called radicand. Radicand. So everything that is under the root is called radicand. So if I have, for example, the square root of x plus 1 plus 3, the radicand is only this. 3 is not part of the radicand because it's not under the square root. Norville, do you have this? Okay. So we can go back now and fill in. I wasn't lazy. I just specifically left them open so you can write them in on your own. So radical notation, the nth root of a to the mth power equals, and now this is the conversion. So the nth root of a to the mth power can be written as an exponential notation with a fractional exponent, or with an exponent that is a fraction. The index is always the denominator. The power is always the numerator. And I can always go back and forth. If you give me this, then I know it's a radical. If you give me this, I know that I can write it as an exponential notation with a base. Of course, this is the base. And this is the fractional. It's a fraction, fractional exponent. So if you say, what about a to the third power? Well, a to the third power is not a radical. But if you say a to power 2/3, then I'll say, yes, this is a radical. Which radical? Which index? Very good. And which power do I keep for a? Sorry, 2. Thank you. Very good. So as you see, the radical can be changed into this. Exponential notation with a fractional exponent. The exponential notation with a fractional exponent can be changed into a radical. So then I can go back to the handout now and fill it in. How will I write the nth root of a to the mth power? I will write a raised to m over n. In other words, I forgot a comma in there, forgive me. In other words, any radical expression can be replaced by an exponential notation. Yes, you're on the right track. By an exponential notation with very good. With a fractional with a fractional exponent. With a fractional exponent. An exponential notation with a fractional exponent. In the radical notation, the index is denoted by lowercase n. Lowercase n. Possible natural numbers for the index are perfect. The quantity or the expression under the radical symbol is named radicand. Yes. Yes. Natural numbers. Yes, Becky?
It says index is that denoted by n or
Lowercase n is right here. The index is in front, at the upper corner, left upper corner of the radical. So that's lowercase n. Okay, example of radical expressions. Square root of 9 is, since 3 raised to the power that is the index. What is the index? By convention, we do not write 2. If there is a radical, or you see a radical with nothing as the index, it's 2, which is the smallest possible index. So 3 raised to this index. What is the index again? 2. Since 3 squared equals 9. Perfect. The cube root of negative 8 is negative 2. Since negative 2 raised to which power? Which is the index? Yes, equals negative 8. The fourth root. The fourth root of 16 is 2. Since 2 raised to the fourth equals perfect. Finally, and we can go on forever, but I stopped at the fifth root. The fifth root of 32 is 2. Since 2 to the fifth equals 32, indeed. Now, please look at the indices from these 4 examples and say, okay, they are blah and blah indices because they are 2 different categories and they are so different. Thank you. Very different. Very different. We did graph one function in Unit 1. Can anyone remind us which radical function we graphed about a few weeks back? We graphed this, we graphed the line, and we graphed this. Which function was this? Square root. Yes. So we graphed an odd index or an even index. Even, because it was a square root. And what did I say about the square root? Not friendly. Why? Why did I call it not friendly? Because it was not defined on all real numbers. The absolute value, friendly. The linear function, friendly. The square root, not. Perfect. Change the radical expressions into an exponential expression with rational exponents. Simplify completely. So let's try. The square root of 2 to the 10th. Copy 2, and what will be the power? The power, 10 over 2. Very good. 10 over 2. So this is 2 to the 5th power, and you can write 32. What about the cube root of negative 3 to the 9th power? Because it's the cube root, I can copy negative 3. And what will be the power now? Where does the power come from?
9 over 3.
9 over 3, excellent. So this is negative 3, and the power is 9 over 3, which is 3. And I will raise negative 3 to the third power. Negative 3 times negative 3 times negative 3. And what do I get? Very good. Excellent. And finally, here, be very careful. These are very different. So let's come back for a second. Here on the square root, I had a positive number. With the fourth root, I had a positive number. But with the cube root, I was able to take the cube root from a negative number and also from a positive number. This is the fifth root. So odd, odd, positive or negative, it's okay. But for the square root, I cannot, or the fourth root, I cannot put in, exactly as Matthew said, I cannot put a negative number because we graphed that function. We graphed this function before, the square root of x. So then, here I have to be careful. The cube root, friendly. If this is a negative number, the answer will be a negative number. But here, you cannot. This will be incorrect to write negative 3 to 4 over 4. Why? Because the fourth root, remember the range and the domain of that function. What was the range? Right. So I can never get a fourth root or the square root to equal a negative number. So this will be a mistake. So what I have to do first for even indices, I have to simplify it under the index. I have to simplify the radicand first. So how much is negative 3 to the fourth power? Negative 3 times negative 3 times negative 3 times negative 3. I'm multiplying 4 negatives. So it has to be positive. So it's 81. And now I simplify it. So you can say now or write it as the fourth root of 3 to the fourth if that's easier for you. And yes, I can copy the base and I have 4 over 4, which is power 1. See the difference between these two? One more time. Here I didn't have to do anything. I just copied the number because the cube root, if the cube root is applied to a negative number, the answer is negative and I'm fine. But the fourth root cannot be applied to a negative number. And it's not, because negative 3 to the fourth is positive 81. But I cannot just simply copy the number like I did with the cube root. I have to simplify inside. I did. I raised negative 3 to the fourth power. Then I can change it back now, 81 into 3 to the fourth, copy the base, and divide the exponents. So careful with even indices. So now here's our note. Radicals with blah indices cannot be applied to blah. What am I supposed to write? Radicals with even indices cannot be applied to, very good, negative numbers. I can apply an odd index to a negative number. I can apply it to positive numbers or 0. But when it comes to even indices, only to 0 or positive. Remember that graph always. Starts at 0, it goes that way. That's the reason why. Okay, the answer will not be a real number. We don't know that yet. This is coming up in chapter 11. Okay, so the answer, if we want to take the square root from negative 4, that will, and see, well, actually, the answer will, yeah, for such situations, true, but also in complex numbers, okay? True. So the answer will not be a real number. It will be a complex number, but we'll find out that. See chapter 11 for situations when we take square roots from negative numbers. Okay. Very good. Let's go to the next page, and I have to get another handout because I can't read. I wrote on top of it. I know I have more. I know I have more. I brought more in here. Oh, I can't seem to find them, and I don't want to waste your time. Okay, so let's start. So change the exponential expression with rational exponents into radical expressions. So now we have expressions that are exponential, they have a base, and they have an exponent that is a fraction, and now we want to go back and change it into a radical. So I will not write on this because I can read it. So we have 3 raised to 2/3. How do I change this? First of all, is it a radical? The answer is yes, because the exponent is a fraction. That's why this is a radical. So have an index, and I have a radicand. What is the index?
3.
So what is inside, or the radicand? Base 3 squared. Very good. So this will be the cube root of 9. Perfect. What about 2 raised to 1/2? That's our next.
Could you just write the square root of 2?
I have to. This is it. Very good. It is. Okay, here's our first, I should say second actually, but the first rule, other than changing from a radical into an exponential notation and from an exponential notation back to a radical. This is our first rule, the product rule. So the nth root of A multiplied by B. This can be written as, please put it in, the nth root of A multiplied by the nth root of B. So now, in other words, the radical of a product is, the what is this? What am I pointing to? The product of, one more time, the radical of a product is the product of, exactly. So in other words, the radical of a product is the product of the radicals. In other words, the radical of a product is the product of the radicals. Easier to remember. Any questions? Okay, so let's see how we apply this. And we have the cube root of 8x cubed. I am asked to simplify this, of course. Is this a product? Good. So then I am allowed to do this. So the radical or the cube root of a product is the product of the cube roots. I do know what the cube root of 8 is, and that is 2. I do know how to simplify the cube root of x cubed, and that is
X.
That's it. It's x to power 3 over 3, which is 1. So the simplified form is 2x. Excellent. Thank you. Here's our next rule, which is the quotient rule. Can you come up with this rule? Just a wild guess. It's not going to be wild. I'm sure you know what you're going to say. The nth root of a ratio. So the radical of a ratio is the ratio of the radicals, of course. So the radical of a ratio is the ratio of the radicals. So you can put it in. So it's the nth root of A over the nth root of B. In other words, comma, for some reason I left all my commas out. The radical of a ratio is the ratio of the radicals. So in other words, the radical of the ratio is the ratio of the radicals. So I would like to simplify the following. Square root of 4 over x to the 4th. Which rule applies here?
Quotient.
The quotient rule. So then I will have the square root of 4 over the square root of x to the 4th. And the top will be, and the bottom will be Very good. 4 divided by 2. Copy the base and divide 4 by the index, which is 2. Very good. And this is the simplified form. Okay. So now this one is what I can read because of the back. So we have to be very clear with this, because maybe I should, next time I should put this rule on our agreement. So the square root of 9 plus, let's say 100, does not equal the square root of 9 plus the square root of 100. The square root of 9 minus 4 does not equal the square root of 9 minus the square root of 4. So the point I'm making with this, I'm emphasizing the fact that if the radicand is a product, I can split it into 2 radicals. If the radicand is a ratio, I can split it into 2 radicals. But if the radicand is a sum or the radicand is a difference, I am not allowed to separate the radical. So please write that the nth root of a plus b does not equal the nth root of a plus the nth root of b. It does not. And I'll give you an example. The nth root of a minus b does not equal the nth root of a minus the nth root of b. It does not. So here's the example, right? So what is this side? This side is the square root of 109. And this is the same thing with 109 raised to which power? It's a radical, so the power has to be a fraction. 1/2. See, you cannot write 9 plus 100 raised to 1/2 and say that this is 9 to 1/2 plus 100 to 1/2. This will be a terrible mistake. Because by the order of operations, we have to combine these two and then raise to 1/2. That's why I wrote 109 or 109 to 1/2. So this side is this. But this side is 3 plus 10, which is 13. Well, 13 squared does not equal 109. So that's why this side will never equal this side if the radicand is a sum. The same thing with the difference. This side is 3 minus 2, which is 1, but this one is the square root of 5. Does the square root of 5 equal 1? No. So one more time, because when we get to the distance between 2 points, I'm going to write this, and I'm going to ask you again. Let me write it as x2 minus x1 squared plus y2 minus y1 squared equals the distance squared. We're gonna get to this in towards the end of this chapter actually. And I'm gonna take the square root from both sides, and I bet at least one person or one student will say, oh, take the square root and this is x2 minus x1 plus y2 minus y1. No. Because the radicand is a sum. So I cannot simplify it ever. It has to stay as a sum. No one can simplify this. The square root of a sum of 2 quantities cannot be simplified. So please make a note of this. When we get to that, we'll talk about it again. So the radical of a sum or difference is the sum difference of radicals. Not. That's the key word. Not. The sum is not of radical. The radical of a sum is not the sum of radicals. The radical of a difference is not the difference of radicals. Perfect. So the example, the square root of 4 plus 9, what would you say? It does not equal
The square root of
4 plus the square root of 9. It does not. Very good. Now, this is a very important discussion. So let's discuss this before we look at those examples. Okay. Let's suppose I am told, so given, this is given to us, that x is any real number. I want to be able to identify what does the square root of x squared equal to. What do you think? So when I say x can be any real number, what are the possibilities on the real number line? What are the possibilities? Negative, 0, or positive. There is nothing else, right? So let's say you're gonna give me an answer here, I'm sure. So then let's say we're gonna check with x equals 4 and x equals 0, and let's say x equals negative 3. So what do you think the answer is? I'm told x is any real number, and I want to take the square root from x squared. What will you say? Which, based on what we discussed, will make sense. What will you say? No, no numbers yet. You're way ahead of me. What will you say? Yes, right? Because you are going to say x to power 2 over 2, because this is the 2 in there that is silent, if you want, or invisible, I should say. So 2 over 2 is 1. This is what you would normally say, correct? Based on what we looked at so far. Now stay with me, because here's the question. Now let's suppose x is 4. So then I have the square root of how much is 4 squared? 16. And then I replace x by 4. Is this true? Yes, so this works. Now I'm going to replace x by 0. So how much is 0 squared? 0, and I replace x by 0. I have to replace it by the same quantity. Is this true? Okay, so this works. Now stay with me. So now I replace here x by negative 3 and here x by negative 3. So then, is this true? No. What is the left-hand side? Forget about the right-hand side. What is the left-hand side? 9, right? A square root of 9. But the square root of 9, does this equal negative 3?
No.
So let's come back to our relation. Something needs to change here so that this works for any real number. And remember, the graph has to have what range? The square root of whatever. What is the range? Right. But look, when I plug in a negative number, this equals a negative number. So this is always positive, unless it has a minus in front, but that's a different story. So this is always positive. What is the adjustment I have to make here on this side to make sure that this is forever positive? I need an adjustment there. What is the adjustment that I need on the right-hand side to make the right-hand side positive forever? What is the right-hand side missing? Think in terms of chapter 9 that we just finished. Exactly. Absolutely, you're right. That's exactly what it needs. Will this make it always positive no matter what?
Yeah.
Yes, it will. And that's the answer. True. So now, this is true for any real number. It's definitely true for 4. It's definitely true for 0. And will it definitely be true for negative 3? Of course. Because the left-hand side is the square root of 9, which is 3, and the right-hand side is 3 as well. So, the correct relationship is when x can be any real number, the square root of x squared is not plain x. It must be the absolute value of x. So before we look at the examples on the handout, I would like to ask you this question. What about the square root of x to the 4th? What is this? Good. Question. Does it need absolute value? Does x squared need the absolute value? Or is it always positive and it does not need the absolute value? It's always positive. Okay, stay with me. Perfect. So I'm assuming that that x is a real number, any real number. What about this? What will the answer for this be? Assuming x is any real number. So what do I write? Question for you. If x is negative, can this be negative? Yes, it's not the same situation. Since this can be negative, what does it need to make it for sure and forever positive? Absolutely. Yes. What about this? And before you say anything, I will remind you, you cannot breach our contract. Here's what I want to write. I want to write this. Yes or no?
No.
Absolutely not. Absolutely not. Because the radicand is a sum of terms. This will be absolutely impossible. Good. Then what I can do is use my contract. What contract? What am I referring to? What am I going to do? Yes. How do I factor this? Yes, you do. Good. Now I'm told x can be anything. What do I do with this? What is the answer? I copy the base. I divide the exponents 2 by 2. What do I get? 1. If this can be negative, I need the absolute value. If it cannot be negative, it can stay by itself without the absolute value. Can it be negative if x is negative 5? So what does it need?
Absolutely not.
Very good. Final thing, and then we go to back to what about this? And before you give me the answer, I want to go back to my first page where we wrote radicals with even indices cannot be applied to negative numbers. So I need the answer to this. And also, I want to draw your attention to the fact that the cube root of negative 8 is negative 2. So, what will be the answer, assuming x can be any real number?
The absolute value of x.
There is no need for the absolute value when the indices are odd. Because if this quantity is negative, the answer will be negative, and it's okay. If this quantity is positive, the answer will be positive, and it's okay. So that's our note. Odd indices, friendly. LY. No headache. No restrictions. Domain all real numbers. No problems. The answer can be whatever. The inside can be whatever. The even indices, a big headache. The inside has to be greater than or equal to 0. The outside has to be greater than or equal to 0. But odd indices, friendly. Can be positive, 0, negative, positive, 0, or negative. For an even index, this is positive or 0, and the answer has to be positive or 0. We graphed this and we saw its range as well. Big headache, no problem. Good. So now let's look at these examples. So, if x is any real number, then there are three possible outcomes, depending on the type of radical and radicand as well. So the nth root of x to the nth power is the absolute value of x if x is any real number. Yes, there are three possible outcomes. Yes. So the nth root the nth root of x to the nth power is the absolute value of x if, yes, x is any real number. The second option is the nth root of x to the n equals, if x is any real number and n is even. The n root of x to the nth is x if x is any real number and n is odd. Excellent. So let's write those two. So you don't have to repeat the x is any real number, right? So you have to write the nth root of x to the nth is the absolute value of n, absolute value of x, if n is even. That's good enough because we already have stated that x is any real number. The nth root of x to the nth is x if n is odd. And now the third possibility that we already discussed. What is the fourth root of x to the 8th equal to? X squared. And I should write here, since x squared is always greater than or equal to 0, comma, although the index is even, but the answer can never be negative. So since x squared is always greater than or equal to 0, there is no need of what on x squared? Yes. On x squared. These are the three possibilities. If x is any real number and the index is odd, don't bother with absolute value. If x is any real number and the index is even, then you have to use the absolute value only if the answer requires it. That's the bottom line. So the nth root of x to the nth is the absolute value of x if n is even. The nth root of x to the n is x if n is odd. And if I have this situation, x to the 6th, 6 divided by 2 is 3. Therefore, x to the 3rd I know could be negative. That's why I need the absolute value on it. And if I have, let's say, the fourth root of x to the 8th, the answer is x squared, even if the index is even. But because this quantity is always positive, there is no need of absolute value on x squared. So these are the three possibilities. And now we're ready to look at these three examples. What will you say about the first example? Square root of x minus 3, everything squared. We are told assume radicands can be negative. Simplify the radicals. Absolutely. Next one. Any questions, please ask. What will this equal to? What about the absolute value? No need. Why? The index is odd. Very good. And what about the next one? Square root of x squared minus 8x plus 16. I want to separate it into the square root of x squared minus the square root of 8x and plus the square root of 16. Yes or no? Absolutely not. So what is my only chance to simplify this radical, if it's possible at all? If at all is possible. What? Very good. X minus 4 everything squared, and the answer would be, of course, because x minus 4 comes out with power 1, and if x is negative, then, and it can be because it's any real number, if it's from 20 above or 4 and above, then this is going to be always positive, but x can be any real number, it can be a negative number, so x minus 4 will be negative. So this is another remark. We already discussed this, but I would like to put it in. If the radicand was obtained from positive numbers only, then there is no need of absolute value for which type of radicals? Even, because we never use for odd anyway. So if the radicand was obtained from positive numbers only, then there is no need of absolute value symbol for even radicals. I should say even indices. Radicals with even indices. Better. All power rules apply to radical expressions. All power rules. So let me give you, I should say exponential rules better here. Exponential. It's the same. Exponential or power is the same. But maybe that's better for you. So all exponential or power rules apply to radical exponent. Okay, so a to the nth times a to the nth. What is the rule for this? Copy the base, and what happens with the exponents? A to the mth times a to the n. And m and n can be fractions now. But what is the rule? I copy the base, and what happens with the exponents? Careful, that will be when I raise a power, an exponential notation to another power. That's when I copy the base and multiply them. So in this case, I copy the base, and what happens to m and n? Very good. M plus n. When I divide, a to the mth power over a to the nth power. I copy the base, and what happens to the exponents now? Yes, in this case I subtract, and always in this order. From the exponent of the top, I subtract the exponent of the denominator. Okay, the next one. A raised to m, everything to the nth power. We are reviewing these rules, but they can be applied to fractions. So it's the same rule. So copy the base, and we multiply. M multiplied by n. What if we raise AB, a product raised to the nth power? Then each factor inside has to be raised to that power. Not to be confused with our agreement. Remember, I said this. And this is not the same with this. This will be the same with this. So AB to the nth power, I have to raise A to the second power and B to the second power. Same thing here. A to the nth multiplied by B to the nth power. This is totally different. This one has two terms. It's a binomial. This is a monomial. This is one term, and this is one term. They cannot be the same. This is a sum of two terms. How many terms do I get when I raise a binomial to the second power? And we have an agreement in the last 5 weeks or so. How many terms? Exactly. So please, because I from my past experience, I saw that many students confuse this with this. And they say, oh, this is a squared plus b squared. It's not. So one term, a product raised to the nth power, each factor has to be raised to that power, like this. Here, this is a sum of two terms, or a difference of two terms. That gives us 3 different terms that we know. Okay. A over b raised to the nth power. A over b raised to the nth power. a raised to the n over b to the nth power. Of course, b cannot be 0. We know that. What about a raised to 0? Careful. Don't say anything yet. So I want to create a raised to 0. Let's say 3 to the 4th power over 3 to the 4th power. I copy the base, and what is the exponent? 0, right? 4 minus 4, right? 0. But what do I know about 81 over 81? This is 81 and this is 81. How much is 81 divided by 81? Right. So any number that is not 0, any number that is not 0 raised to 0 is 1. So this is a very important assumption. A is not 0. 0 raised to 0 is not 1. Okay, and finally, a to negative n. Of course, a is not 0. So what do I replace this by? Very good. 1 over a to the nth power. Very important property is the one that we just discussed a few minutes ago. I said 2 to negative 1 is the same with 1/2. And this is this property. Give me just 1 second to stop this.